New physics. The law of universal gravitation was stated by Newton in his book, Philosophia Naturalis Principia Mathematica, published in London during 1687. This law from the very beginning received two formulations, one scientific, the other popular. The scientific formulation is as follows. There are observed phenomena between two bodies in space that can be described by presuming that two bodies attract one another with a force directly proportional to the product of their masses, and inversely proportional to the square of the distance separating them. The popular formulation is: two bodies attract one another with a force directly proportional to the product of their masses, and inversely proportional to the square of the distance separating them. In this second formulation, the fact is entirely forgotten that the force of attraction is merely a fictitious quantity, accepted only for a convenient description of phenomena. The force of attraction is regarded as really existing both between the sun and the earth, and between the earth and a falling stone. More recent electromagnetic theory of gravitational fields dogmatizes this second view. Professor ch42 writes in his textbook on physics, see Volume 1, page 182. The tremendous development of celestial mechanics, entirely based upon the law of gravitation taken as a fact, made scientists forget the purely descriptive character of this law, and see it in the final formulation of an actually existent physical phenomenon. What is important in Newton's law is that it gives a purely simple mathematical formulation that can be applied throughout the universe, and on the basis of which it is possible to calculate all movements, in particular the movement of celestial bodies, with astonishing accuracy. Newton certainly never established it as fact that bodies are actually attracted by one another, nor did he establish why they are attracted, or through the medium of what. How can the sun influence the motion of the earth through the void of space? How in general is it possible to conceive action through empty space? The law of gravitation does not give an answer to this question, and Newton himself was perfectly aware of this fact. Both he and his contemporaries, Huygens and Leibniz, gave warning against an attempt to see in Newton's law the solution to the problem of action through empty space, and regarded this law merely as a formula for calculation. Nevertheless, the tremendous achievements of physics and astronomy attained through the application of Newton's law caused scientists to forget this warning, and the opinion was gradually established that Newton had discovered the force of attraction. Professor ch42 writes in his textbook on physics, see Volume 1, pages 181, 182 and 183. The term axio in distans, that is, action at a distance, designates one of the most harmful doctrines that ever prevailed in physics, and retarded its progress. This doctrine admitted the possibility of immediate action from one object on another at a certain distance from it, at a distance so great as to make immediate contact between the two impossible. In the first half of the 19th century, the idea of action at a distance reigned supreme in science. Faraday was the first to point out the impossibility of the admission that a body should without mediation excite forces and produce motion at a point where the body is not situated. Leaving aside the question of universal gravitation, he turned his special attention to magnetic and electrical phenomena, pointing out the supremely important part played in these phenomena by the intervening medium, which fills the space between the bodies that appear to act upon one another without mediation. At the present time, the conviction that action at a distance should not be admitted in any domain of physical phenomena has obtained universal recognition. The old physics was able to abandon action at a distance only after it had replaced the hypothesis of the universal medium or ether. The acceptance of that hypothesis was equally necessary for the theories of light and electrical phenomena, as they were understood by old physics. In the 18th century, phenomena of light were explained by the hypothesis of emission put forward by Newton in 1704. This hypothesis assumed that luminous bodies emit in all directions minute particles of a special light substance that travel through space with tremendous velocity and, entering the eye, produce in it the impression of light. In this idea, Newton developed the ideas of the ancients. In Plato, the expression, "light filled my eyes," is often found. Later, mainly in the 19th century, when the attention of investigators was drawn to those results of the phenomena of light that could not be explained by the hypothesis of emission, another hypothesis obtained wide recognition, namely the hypothesis of undulatory vibrations in ether. This hypothesis, first advanced by the Dutch physicist Huygens in 1690, was not for a long time accepted by science. Later, investigations of the phenomena of diffraction definitely turned the scale in favor of the hypothesis of light waves as against the hypothesis of emission. The subsequent work of physicists, mainly on the polarization of light, for a time gained general recognition for this hypothesis. In this hypothesis, the phenomena of light are explained as analogous to the phenomena of sound. Just as sound results from the vibration of particles of the sonant body, and is propagated through the vibration of particles of the air or some other elastic medium. So on this hypothesis, light results from the vibration of molecules of the luminous body, and is propagated by means of vibrations in an exceedingly elastic ether, which fills both interstellar space and the space between molecules. During the 19th century, the theory of vibrations gradually became the basis of the whole of physics. Electricity, magnetism, heat, light, even life and thought, purely dialectically it is true, were explained by the theory of vibrations. It cannot be denied that in the case of the phenomena of light and electromagnetics, the theory of vibrations gave remarkably convenient and simple formulae for calculation. A whole series of remarkable discoveries and inventions were made on the basis of the theory of vibrations. However, the theory of vibrations required ether. Ether as a hypothesis was created for the explanation of very heterogeneous phenomena, and it was therefore endowed with strange and contradictory properties. It is omnipresent, it fills the whole universe, pervades all points, all atoms, and all interatomic space. It is continuous, it possesses perfect elasticity. Yet ether is so rarefied, thin, and permeable, that all earthly and heavenly bodies pass through it, without meeting with perceptible resistance to their movement. Its rarity is so great that if ether were to be condensed into a liquid, the whole of its mass, within the limits of the system of the Milky Way, could be contained in 1 cubic centimeter. At the same time, Sir Oliver Lodge considered the density of ether to be approximately 1 billion times greater than the density of water. From the latter point of view, the world proves to be composed of a solid substance, ether, which is millions of times denser than a diamond. Matter, even the densest matter we know of, is merely empty space, a bubble in the mass of ether. Many attempts have been made to prove the existence of ether, or to discover facts confirming its existence. Thus it was recognized that the existence of ether would be established, if it were once proven that a ray of light, moving faster than any other ray of light, changed its character in a certain way. It is known that the pitch of a sound rises or falls as the hearer approaches or retreats from it, Doppler's principle. Theoretically, this principle was considered applicable to light. This would have meant that a swiftly approaching or retreating object would change its color, as the sound of a locomotive engine whistle changes its pitch as it approaches or retreats. However, owing to the structure of the eye and the speed of its perception, it was impossible to expect that the eye would notice the change in color, even if such a change actually took place. In order to establish the fact of the change of color, it was necessary to have some recourse to a spectroscope, that is to decompose a ray of light, and observe the displacement of the lines of the spectrum. To verify the above ideas, the American scientists Michelson and Morley began a series of experiments in the 1880s. The experiments were carried out with the aid of a complicated installation, over a period of many years. See the American Journal of Science, 3rd series, published in 1887, volume 34, pages 333 and those that follow. The apparatus was mounted on a stone slab fixed upon a wooden float revolving in a tank filled with mercury, and made 1 revolution in 6 minutes. A ray of light from a special lamp fell upon mirrors attached to the revolving flat, and partly passed through them, partly reflected. One half going in the direction of the movement of the earth, and the other at right angles to it. This should have given a noticeable displacement of the interference fringes, consequent upon the change of the velocity of light relative to the ether, as one half of the ray moved at the velocity of light plus the velocity of the earth, while the other moved without this additional velocity. Both halves of the ray, the half that was reflected, and the half that was allowed to pass, were caught by a system of mirrors, and thrown onto a mirror, which then united the 2 halves, and thus made it possible to observe whether displacement had taken place or not. Observations were made over a long period at all times of the day and night, and no alteration in the interference fringes was discovered. This fact was taken as an unexpected proof that there exists no relative movement between the Earth and the ether, and as a confirmation of Fizeau's experiment that had shown the impossibility of increasing the velocity of light by means of movement in the medium in which it is propagated. From the standpoint of the original problem, it was necessary to recognize that the experiment failed. However, it disclosed another phenomenon, possibly much more significant than that which it attempted to establish. This was the fact that the speed of a ray of light cannot be increased. The ray of light moving with the Earth differed in no way from the ray of light moving at right angles to the direction of the movement of the Earth in its orbit. It was necessary to recognize as a law that the velocity of a ray of light is a constant and limiting quantity that cannot be increased. Which in its turn explained why Doppler's principle was inapplicable to phenomena of light. At the same time, establishing the fact that the general law of the composition of velocities, that was the basis of mechanics, could not be applied to the velocity of light. This would mean that, for example, if we imagined a satellite moving at the rate of 30 km per second, i.e. with the velocity of the movement of the Earth, then a ray of light overtaking or meeting with it, the composition of velocities would in this case be impossible. The velocity of light will not be increased by the addition to it of the velocity of the satellite, and will not be decreased by the subtraction from it of the velocity of the satellite. In other words, the ray of light will light up both the front and the back of the spacecraft simultaneously. Furthermore, this will happen simultaneously and independently of whether the satellite is retreating from the source of the light, is stationary, or is moving towards it. At the same time, it was established that no existing instrument or means of observation could intercept a moving ray of light. In other words, it is not possible to catch the end of a ray that has not yet reached its destination. In theory, we may speak of rays that have not yet reached a certain point, but in practice we are unable to observe such rays. Consequently, for us, with our means of observation, the propagation of light is virtually instantaneous. At the same time, the physicists who analyzed the results of the Michelson-Morley experiment explained its failure by the presence of new and unknown phenomena resulting from great velocities. The first attempts to solve this question were made by Lorentz and Fitzgerald. The experiment could not succeed, was Lorentz's formulation of his propositions, for every body moving in ether itself undergoes a deformation, namely for an observer at rest, it contracts in the direction of the motion. Basing his reasoning on the fundamental laws of mechanics and physics, he showed by means of a series of mathematical constructions that the Michelson-Morley installation necessarily suffered a contraction. That the amount of the contraction was exactly such as to counterbalance the displacement of the light waves consequent upon their direction in space. Hence annulling the results of the difference in the velocity of the two rays. Lorentz's conclusions as to the presumed contraction of a moving body gave rise in their turn to many explanations, one of which was put forward from the point of view of Professor Einstein's special principle of relativity. However, this relates to new physics. The old physics was inextricably linked with the theory of vibrations. New theory that came to replace the mechanical theory of vibrations was a theory of the atomic structure of light and electricity, taken as independently existing matters composed of quanta. The new teaching, notes Professor Troelsen, appears to be a return to the Newtonian emission theory, although considerably altered. This new teaching is far from being completed, as its most important part, the quantum itself, still remains undefined. What a quantum is, cannot be defined by new physics. The theory of the atomic structure of light and electricity entirely altered the view on electrical and light phenomena. Science has ceased to see the fundamental cause of electrical phenomena in special states of ether, and has returned to the old doctrine that admitted electricity to be a kind of substance which has real existence. The same thing has happened with light. According to modern theories, light is a stream of minute particles, photons, rushing through space at the rate of 300,000 km per second. It is not the corpuscles of Newton, but a special kind of matter energy, formed by electromagnetic vortices. The materiality of the light stream was established by the experiments of Professor Lebedev of Moscow. Professor Lebedev proves that light has weight, that is to say that light when falling on bodies, produces a mechanical pressure on them. It is characteristic that at the beginning of his experiments to determine the weight of light, Professor Lebedev based them on the theory of vibrations of the ether. This shows how the old physics confuted itself. Professor Lebedev's discovery was very important for astronomy. For instance, it explained certain phenomena that had been observed at the passing of the tail of a comet near the Sun. But it was chiefly important for physics, as it supplied a further confirmation of the unity of the structure of radiant energy. The impossibility of proving the existence of the ether, the establishment of the limiting and constant velocity of light, new theories of light and electricity, and above all the study of the structure of the atom, indicated the most interesting lines of development of new physics. Another part of new physics has developed from that particular formation of physics that was called mathematical physics. According to the definition that was given to it, mathematical physics usually started from some fact confirmed by experiment, and expressing a certain orderly connection between phenomena. It enveloped this connection in a mathematical form and further, as it were, transformed itself into pure mathematics, and began to elaborate exclusively by means of mathematical analysis, those consequences which followed from the basic proposition, as noted by Professor ch42. Thus it is presumed that the success or failure of the conclusions of mathematical physics might depend upon three factors. First, upon the correctness of the definition of the fundamental fact. Second, on the correctness of its mathematical expression. Third, on the correctness of the subsequent mathematical analysis. Professor ch42 writes in Volume 1, on page 13. There was a time when the importance of mathematical physics was greatly exaggerated. It was expected that it was precisely mathematical physics that should have served the principal course of the development of physics as a science. This, however, is quite erroneous. In the deductions of mathematical physics there are a great number of essential defects. In the first place, in almost every case, it is only in the first rough approximation that they correspond with the results of direct observation. This is caused by the fact that the premises of mathematical physics can be considered sufficiently exact, only within the narrowest limits. Furthermore, these premises generally disregard a whole series of collateral circumstances, the influence of which, outside these narrow limits, cannot be neglected. Therefore, the deductions of mathematical physics correspond to ideal cases, that cannot be practically realized and are often far removed from actuality. And further, it should be added that the methods of mathematical physics make it possible to solve special problems in hardly any but the simplest of cases, particularly in so far as the form of the body is concerned. But practical physics cannot limit itself to these cases, and is continually faced with problems which mathematical physics is incapable of solving. Furthermore, the results of the deductions of mathematical physics are often so complicated as to prove their practical application impossible. In addition to this should be added another characteristic property of mathematical physics, namely that as a rule, its deductions cannot be formulated other than mathematically, and lose all their meaning and importance if an attempt be made to interpret them in the language of facts. The new physics that developed from mathematical physics possesses many of the properties of the latter. Professor Einstein's theory of relativity is a separate chapter in new physics, which has developed from mathematical physics. It is wrong to identify the theory of relativity with new physics, as is done by some followers of Professor Einstein. New physics can exist without the theory of relativity. But for us, from the standpoint of the construction of a model of the universe, the theory of relativity is of great interest, because it deals before anything else with the fundamental question of the form of the world.